This is lesson 1-8, sets of numbers. To begin, we need to identify what a set is. And a set is just a group of things that we put together that have something in common. 99% of the time, when we put these groups of things together, it is numbers that have a specific characteristic. For example, the set of even numbers is 2, 4, 6, 8, 10. And those three dots mean and so on because we can just continue to add to the set of even numbers with more numbers. In fact, that set is called an infinite set. Whereas a subset is a set of numbers, and the subset is usually a smaller set. It can't ever be bigger, and it's made from the other set. For example, if I did the set of single-digit even numbers, we have 2, 4, 6, and 8, and that's considered to be a finite set because that has a countable number of things in that set. These are the common sets that you should know. For example, the first one, counting numbers, starts with 1 and you continue to go up. Whole numbers is a little bit bigger set than counting numbers. It just adds 0 in the front. Integers are all of the whole numbers and they're opposites, so it includes negatives. When you have the set of integers, you want to think about what a number line looks like. And then we have two bigger sets, the rational numbers and irrational numbers, and we will talk about those more at length as we continue these notes. So what do rational numbers look like? A rational number is any number that could be an integer, and since integers are a bigger set than the whole numbers and counting numbers, meaning the counting numbers and whole numbers are subsets of the integral set, they are also rational numbers. A fraction, any fraction, is a rational number. And a repeating decimal is also a rational number. I gave you a couple of examples of repeating decimals there that you should know off the top of your head. Irrational numbers have to have the following properties. It has to be a decimal or a non-perfect square root. So if you take the square root of something that's not a perfect square, it's an irrational number. It has to be a non-stop decimal that's not repeating. It can be patterned, but it isn't necessarily repeating. Here's some examples. Tell whether each number is rational or irrational. Pause the video at this point to give yourself a chance to try on your own. Here are your answers. 3.2, because it's a decimal that stops, is a rational number. The next one, that long, drawn-out decimal there, that does not have a pattern to it at all whatsoever, a repetition to it at all whatsoever, that is irrational. The third one, even though it's a longer decimal, it does stop, so that is rational. The next one, 23/45, is a fraction, so it is rational because all fractions are rational. And finally, pi is the most famous irrational number. It's a decimal that goes on and on forever. So things to know about operations when you're dealing with rational and irrational numbers. If your situation presents itself that you have two rational numbers and you are adding, subtracting, multiplying, or dividing, your result will always be rational and there are no exceptions to that rule. However, if you have irrational numbers, you have to evaluate the sum, difference, product, or quotient first, and then decide if it's rational or irrational based on what you see. Finally, if you have one of each, a rational number and an irrational number, the result will always be irrational with one exception. Anytime you multiply by 0, your answer will be rational because your answer is 0 according to the 0 property of multiplication. And finally, just a review of absolute value. The absolute value of any number, and that is the symbol, with n being a number, is the distance between that number and 0 on the number line. Breaking it down more simply, it's as simple as this. If your number inside the absolute value bars is positive, leave it alone. If the number is inside is negative, make it positive. And anytime you're working with absolute value, you want to treat the absolute value as if it was a set of parentheses, meaning you want to perform any operations inside your absolute value first before applying the absolute value function. If you're having any issues in any portion of this lesson, please make sure you are emailing me or consulting me in class.